Quantum theory provides a foundation for theoretical physics that is extremely predictive and explanatory. As per the Stanford Encyclopedia of Philosophy, the theory is an extraordinarily well-functioning algorithm for predicting and explaining the outcomes of observations, but there is no agreement on what form of objective reality may underpin these findings. One class of interpretations hypothesizes backward-in-time causal influences, also known as retrocausality, which is the basis for constructing a convincing foundational account of quantum theory. It proposes that a future event could influence the past, like when someone's stomach gets hurt today because of tomorrow's meal. In 2017, two physicists, one from the United States and one from Canada, examined several basic assumptions in quantum theory, and concluded that measurements made to a particle might reverberate back in time and forward, unless scientists found that time only runs one way. Quantum physics is known to be strange, partly due to the fact that particles, on a fundamental level, do not behave like solid billiard balls sliding down a table but rather like a fuzzy mist of possibilities swirling around the room. In 2012, physicist Hugh Price suggested that if the strange probabilities behind quantum states are genuine, and if nothing confines time to one direction, the black ball in that cloud of maybes might roll out of the pocket and knock the white ball. The two physicists, Matthew S. Leifer from Chapman University in California and Matthew F. Pusey from the Perimeter Institute for Theoretical Physics in Ontario, wondered whether the quantum world would be different when it comes to time. They applied their new model to Bell's theorem to find out. John Stuart Bell said that the universe is random at a fundamental level. That means weird things happening in quantum mechanics cannot be explained by actions taking place in a nearby place. But what about taking place at a certain time? Can something far away influence that cloud without touching it, as Albert Einstein describes it as spooky? Measuring one of two particles linked in space at any point instantaneously establishes the value for the other, regardless of where it has traveled in the universe. This entanglement has been tested several times in light of Bell's theorem, filling gaps that may indicate they are interacting on a local level in some way, despite what appears to be a distance. However, if causality worked backward, a particle might carry the action of its measurement back in time to when it was entangled, impacting its partner. No need for faster-than-light communications. Retrocausality could have vast implications for understanding the foundations of quantum theory. One of which is the implication for Bell tests that shows distant particles cannot influence each other, but quantum theory is incomplete. If Leifer and Pusey's theory is correct, the retrocausality may be one of the missing pieces that complete the quantum theory. Leifer said that the different interpretations of quantum theory have different implications for how scientists generalize standard quantum theory. They might need to construct the correct quantum gravity theory or resolve some high-energy physics issues. He added that if retrocausality does exist in the universe, then it might be the case that there are certain eras in which there is not a definite arrow of causality. The two physicists do not have any experiments to test retrocausality, but perhaps the most needed is theoretical support, as the idea is more an interpretation of observations rather than making new observations.